Welcome you all to the lecture series of Digital Electronics KOE 039/049. Myself Dr. Kishanu Kundu, Assistant Professor, Department of Electronics and Communication Engineering, GL Bajaj Institute of Technology and Management. So, we are in lecture number 29 and we were discussing about digital logic families, right. In digital logic families part 1, we have given a brief introduction of digital logic families. We have talked about the characteristics of digital logic families. So, now today in lecture number 29, we are going to discuss in detail about some few examples of digital logic family. Those are RTL, DTL and DCTL. So, let us move. So, logic gates are main components of any digital circuit, we know that. So, almost all digital circuits are made of logic gates, that also we have seen in previous lectures. These logic gates are made of transistors and other active or passive components. Here transistors work as electronic solid state switches. There are different classes or types of logic families according to which logic gates are built. So, the first logic family example which we are going to discuss is resistor-transistor logic, or in brief we can call it as RTL. Resistor-transistor logic is the first digital circuit to construct the logic gates. It is also known as transistor resistor logic or TRL. Here the transistor and resistor are used to make the logic gates. From the diagram you can see that here we have one resistor and one transistor. Okay. The resistor is used as the input component. Here the resistor is acting as a input component and the transistor is used as output component. So, resistor is as input and transistor is as output. Here you can see the basic circuit of NOT gate. This is actually nothing but we have implemented NOT gate using RTL logic. Okay. The NOT gate uses RTL logic, also known as RTL inverter, that we have written as RTL inverter. The working of this circuit is very simple. When no voltage is applied to the input, the transistor act as open circuit. The transistor is acting as open circuit. So, the output will be high. When transistor acts as open circuit, transistor output is high, and when the voltage is applied to the input terminal, the transistor act as closed circuit. So, VCC will be grounded and the output of the circuit will be low. And we know that NOT gate is also like that. When we give logic 1 to NOT gate, it gives low output, and when we give low input to inverter, it gives high output. So, same thing we have implemented here using resistor and transistor. So, that is what is called resistor transistor logic. Once again I am telling, when no voltage is applied to the input, so at that time transistor acts as open circuit, and when transistor acts as open circuit, the output will be high. And when the voltage is applied to the input terminal, then the transistor acts as closed circuit. That means the output will be low. Okay. Very simple. The architecture of RTL NOT gate or inverter has been discussed, right. Let us proceed. Now, here we are going to implement a 2 input NOR gate. So, first of all we will check what is NOR gate. NOR gate is like that, right. This is actually NOR gate, and what is the output of NOR gate? A, B. We know if 2 inputs are there, there will be 4 combination 0 0 0 1 1 0 and 1 1. Okay. So, for NOR gate we will be having this. When both the inputs are 1, then only we will be having 0 output, rest of the case we will be having 1 second 1 0, okay, this is also 0. Okay. So, when both the inputs are low, then only we will be getting high output, rest of the cases we will be getting 0 output. This is actually NOR gate. So, this thing we are going to implement using RTL logic. So, let us proceed. So, here you can see we have taken two resistor R1 and R2, two transistor Q1 and Q2, and here one another resistor RC. Okay. RC is connected to the VCC. Here we have connected, we are getting output from the terminals of transistors, and here two resistors are there. Got it? So, let us begin. When both the inputs at A, B are at 0 volt, mean logic 0, then it is not enough to turn on the gates of both the transistor. So, transistor will not conduct. Due to this, the voltage VCC will appear at the output. So, these are cut at that time. So, we will get output from this, right. So, here we will get output at logic 1. Got it? Next case, when any one of the inputs either A or B is high, logic 1, then the transistor with high input get turns on. Means suppose we are having this is 1 and this is 0. So, this will work and this will not work, right. So, this will make the path of supply voltage to go to the ground, right. So, this will work, means it will act as a closed circuit, and the this will be connected to ground, right, and thus there will be 0 volt at the output terminal. Okay. So, that is why we are getting 0 at this condition, we are doing 1 0. So, we are getting output as 0. Got it? Again, if we do the another combination, if we do the next combination, so here 0 and B 1, then this will work and this will not work. So, now this will be short circuited, closed switch, and output will be connected to the ground. So, here also you will be getting 0, and when both the inputs are 1, then both the transistors will be on, and in that case output will be connected to ground via closed switch circuit. So, we will be getting 0. So, here when both the inputs are high, it will drive both the transistor on, it will make a path for the supply voltage to flow to the ground through resistor RC and transistor, therefore, there will be 0 volt at the output terminal Y. So, you can check it that this circuit is perfectly working as 2 input NOR gate, but here in spite of NOR gate we have used resistor and transistor for giving the output. Okay. I think this 2 input RTL NOR gate is very much clear. Let us proceed. So, now we will discuss the advantages and disadvantages of RTL. So, what are the advantages? It is the most simple detailed circuit, first one. Next, the minimum number of transistors is required to build the logic circuit other than other logic families. Okay. This is another important point, minimum number. Third is operation of circuit is very simple, that we have just seen, right. So, these are the 3 advantages. Let us discuss about the disadvantages of RTL logic. Very poor response time and high propagation delay. These are the 2 very main cause of not using RTL. Okay. So, the first one is very poor response time and high propagation delay, and second one is power dissipation is high due to the resistors. As we are using resistors, the power dissipation is very much high. Okay. So, these are the advantages and disadvantages of RTL logic. So, now as we are having some disadvantages of RTL logic, we are moving forward to diode transistor logic, that is DTL, diode transistor logic, that is DTL. So, diode transistor logic belongs to the DTL logic family. The logic circuit had diodes at input side and transistor at output side. Previously, we were having resistors at input side and transistor as output side. Now, we are having diodes at input side. Let us check. In RTL logic, we are having resistors as input component, right. Here diodes are used as input components. Okay. So, that is why it is known as diode transistor logic. It has more advantage than resistor logic, obviously that is why we are using. In which case it is having better advantage. The transistor logic has improved noise margin, greater fan out. Already we have discussed about noise margin, fan out characteristic in the previous lecture, lecture number 28. So, you can refer that. Okay. However, the propagation delay is more for this device when compared to TTL, but the speed is better than RTL. Okay. TTL is transistor logic, that we are going to discuss in our upcoming videos, but till so far we have discussed RTL. So, DTL is better than RTL in terms of speed as well as noise margin and greater fan out. Okay. So, now let us discuss a circuit. So, here we have taken a 2 input DTL NAND gate. Okay. So, first of all we will draw the normal NAND gate. We know this is the normal NAND gate circuit A, B, and this is, and what is the truth table 0 0 0 1 1 0 1 1. So, when both the inputs are high, the output is low, and rest of the cases we are getting output as high. So, this is NAND gate logic. Okay. Now, we are going to implement this NAND gate using DTL circuit. Okay. So, let us start. It consists of 2 diodes. We have taken 2 diodes DA and DB. These are the 2 diodes. NPN diode, PN junction diode we are using. Okay. PN junction diode, sorry, not NPN, NPN is transistor. This is PN junction diode, and the resistors R1, we are having one resistor R1. Okay. The common emitter configuration of transistor Q1 and resistor R2 from the output side. Here we are using one resistor R2 and a transistor having common emitter configuration. Okay. And we have again here we have taken one resistor R3. Okay. So, let us proceed. So, we will take the case 1 when both the inputs are low. When both the inputs are low, what is happening at that time? So, let us check. When both A and B are low, the diode DA and DB become forward biased, because this is plus and this is minus, this is plus and minus. So, here we are giving 0 0. So, this is forward biased, the negative terminal of diode, at the negative terminal of diode we are giving 0 voltage. So, this is forward biased. So, when both are low, DA DB are forward biased. So, both diodes will conduct in forward direction. This will conduct, both the diode will be conducting, both the diode will be conducting. So, the current due to the supply voltage VCC will go to the ground through R1. Okay. And 2 diodes RA, DA and DB. The supply voltage gets dropped in the resistor R1 and it will not be sufficient to turn on the transistor. So, will not, this transistor will be not working at that time, right. So, the transistor will be in the cut off mode, the transistor is cut off. You can see from the diagram itself, I am make it faded, right. So, from the diagram itself you can understand that when DA DB both are working, the transistor is not working, right. Therefore, the output at terminal Y will be high value because it is directly connected to the supply voltage, logic 1. Okay. The operation of gate with the current flow path is shown in the figure. You can see the flow of current. Okay. So, this is the first case when both the inputs are low. So, same you can see we are getting high output, means it is resemble with the NAND gate truth table. Next, now if any one of the input either A or B is given to low, which makes the corresponding diode to be forward bias, in this case the same operation will take place. Yes, you can see from it, if any one of the input is low, so what will happen? So, if B is 0 and is 1, so this will work and this will not work. So, this in this case this Y will be connected to VCC and this will be cut off, right. So, in all three cases we will be getting as 1 as output, logic 1. Since any of the diodes is forward bias, the current will go to the ground through the forward bias diode, and so the transistor will be in the cut off mode. The output at any time in Y will be always at logic 1. Okay, got it. Now, we will discuss the case 2 when both the inputs are high, when both are high. So, if we are giving high to both the things, so this you can see that these two diodes are reverse bias. So, if diode are reverse bias, this will be not conducting, open switch, right. So, the now this path will be working, right, and if it is open switch, then current will be going to like this, it will not go to the diode part, it will go directly to the base of transistor, right. So, let us check when both inputs A and B are high, which will reverse bias both the diodes, already I have seen in the diagram. So, both diodes will not conduct, in this case voltage from the supply will be enough to drive the transistor into the conduction mode. Obviously, the current is coming to the base, so it will be working. Thus, the transistor will conduct through the collector and emitter, the entire voltage gets dropped in the resistor R2 and the output of terminal Y, okay, will have low output. So, in that case we will be having Y as 0, which is considered logic 0. This operation is shown in the figure itself. Okay. So, when both the inputs are low, then we are getting output as 1, any of the input is low, we are getting output as 1, but when both our inputs are 1, we are getting output as 0. So, this is nothing but a 2 input DTL NAND gate circuit. Clear? Okay, fine. Now, next we will discuss another example or another family that is belonging to digital logic family, that is called direct coupled transistor logic, that is DCTL, direct coupled transistor logic, that is DCTL. So, let us begin. Direct coupled transistor logic is also called as integrated injection logic or I2C circuit, integrated injection logic I2C. It uses no biasing and loading resistors at all. Resistors require a lot of power and space on the IC chip. Hence, their elimination results in higher density circuit operating at much reduced power. Because of its high speed and lesser power dissipation, it is used in large computers. So, direct coupled transistor is mostly used in large computers. Okay. Such circuit are also used where high packing density is of prime consideration, like digital wristwatches. Nowadays, all of we are using smart watches, right. So, DCTL is having an application is smart watches, right, digital watches, wristwatches. I2L chips are capable of microwatt power dissipation, yet can provide high currents when necessary to drive LED displays. I2L means integrated injection logic, and here we can say integrated injection logic, I square C, I square L both are same. Okay. That is it is also very easy to fabricate. Okay. Now, let us discuss a circuit of DCTL. So, here we have taken one resistors RL load resistor and 3 transistors Q1, Q2 and Q3, and we are taking output from this point. Okay. So, 3 transistors are connected in series to form a NAND gate for positive input signal A, B and C. Okay. It is a NAND gate using DCTL. Previously, we have used DTL logic for explaining NAND gate. Here we are using DCTL. So, no resistor is very less. There we are using 3 resistor, here only 1. Okay. So, let us start. If any of the 3 transistor is off, the output voltage at D will be the supply voltage VCC in the unloaded condition. Under loaded condition, the voltage at D will depend on the resistor RL. This is R, you can see this is R suffix L, this one. Okay. And the VBE is on of the next stage of the transistor. Base to emitter voltage, VB is nothing but base to emitter voltage. Okay. This is base. So, base to emitter voltage, this is base for all the transistor, base. There are 3 terminals of transistor, base, emitter and collector. Okay. Already base transistors actually part of analog circuits, okay, but here in digital circuits also we are using transistor. Okay. So, when all 3 transistors are on, the potential at D will be closer to the ground than in the previous case, and will be in the sum of the VC saturation of Q1, Q2 and Q3, okay, in series. Consequently, the principal disadvantage of this configuration is the necessity to ensure that the next stage transistor will be off when all 3 transistors are on. This is the disadvantage of this circuit. Okay. The sum of the 3 VCE saturation in series must be less than VB on of the next stage transistor. What means of accomplishing this is to supply more base drive to Q1, Q2 and Q3, thereby drawing them further into saturation and lowering the saturation resistance. So, you can see the disadvantage as well. Okay. So, this is the DCTL circuit of NAND gate. This circuit is actually performing like a NAND gate using DCTL logic. Now, previously we have discussed DCTL series gating. Now, we are going to discuss DCTL in parallel gating. Okay. So, let us see, here we are having BCC, 1 load resistor RL, 3 transistor Q1, Q2, Q3 and output is taken from the collector of all the transistor. Okay. So, a parallel DCTL gate which is really previously converted inverter stage with the 3 transistor having individual inputs instead of a single transistor. Okay. Previously it was an AND gate, right. Now, here it is like inverter. Obviously, this configuration is a NOR circuit. So, previously we have discussed as NAND gate, now we are going to discuss NOR gate. Okay. Already we know what is the truth table of NOR gate. Let us check once again. This is the NOR gate, this is the truth table of NOR gate. Okay. Means when both the inputs are low, output is high, and any other input is low, then it will be, or any one be 1, the output is be 0. When both the inputs are low, output is 1. When any of the inputs is high, then output is low. So, this is nothing but the NOR gate. So, here using DCTL parallel gating, we are implementing the NOR gate circuit. So, here you can see if any input is high on any of the 3 transistor, its collector will draw the current through the load resistor, causing the output go to the low. Means if any one of the input of the high is high. Whenever we are giving one input to any one of the transistor, then it will be giving 0 output, okay, just like NOR gate. So, previously we have discussed the series circuit of DCTL getting, and it was acting as a NAND gate, and here we are used DCTL parallel getting to show the working of NOR gate. Okay. So, now disadvantages of DCTL, first is current hogging. One of the most undesirable feature of DCTL is what commonly known as current hogging, and this phenomenon arises because of the spread in VBE of the various driven transistors. No two transistors will ever have identical input characteristic, and it is always desirable to use transistor with as small a production spread as possible on VBE base to emitter voltage. The crosstalk or the noise problem. In high speed system, pulses with fast rise times are likely to produce potential differences in the ground system, mainly because of ground inductances. These voltages are likely to interfere with the stable operation of the system. DCTL systems are very susceptible of these noise voltages because the operating and signal voltages are naturally low in these systems. If several transistors are on one end of the ground system are turned on, the resulting pulse generated in the ground system can supply a positive or negative pulse depending on the polarity, which can cause faulty turn on or turn off of the other transistors further down to the ground system. One solution is to mount the transistor very close to together, thereby minimizing the ground inductances. Beside ground noise, DCTL is also vulnerable to noise on power supplies and stray noises picked up by connecting leads. So, these are the disadvantages, okay. Of the various logic scheme, DCTL has one of the lowest noise margins. You have to make this point very clear. The lowest margin can be achieved by DCTL, typically 0.1 volt at 125 degree centigrade to about 0.2 volt at room temperature, depending on the fan out and whether the transistor is on or off. Okay. So, now after a disadvantage, let us discuss the advantages of DCTL. So, in spite of this severe limitation, DCTL still have several desirable features. Since the voltage swing involved was very small, transistor with relatively low breakdown ratings can be used. The fact that only one power supply voltage is used in very convenient feature, since low voltages are used, sometimes as low as 3 volt power dissipation in both the resistors and the transistor is quite low. Although DCTL systems are expensive in the number of transistor used, the absence of interstage coupling elements, different resistor sizes, clamping diodes and many supply voltage make them relatively simple. Okay. So, they are using only transistors, and transistors are expensive, but rather than transistor, these are not used like coupling elements, resistors, different resistor, clamping diodes, many supply voltage are not there. So, that makes the DCTL use very helpful. So, these are the reference, and thank you.